Um, Good afternoon, everyone. Today we have the pleasure to receive Professor Joe Primack from University of California, Santa Cruz, and he's going to tell us about new insights on galaxy formation by comparing simulations and observations. Thank you very much for accepting this invitation.
I'm glad to do it. It's been a long time since I was last in Rio, and I'm happy to say hi to my friends from there and to the new people that I don't know yet who will be watching this. The outline of the talk is, first I'm going to talk about large-scale simulations. I'm going to talk about a new series of simulations which use the Planck cosmology parameters, and about a new idea that Aldo Rodriguez Puebla, a postdoc with me here in Santa Cruz, and I, and Peter Baruzzi and Sandy Faber have been developing, that we call the SHARC idea, which stands for Stellar Halo Accretion Rate Coevolution. I'll then talk about high-resolution simulations of galaxies. But let's start with the large-scale simulations. Incidentally, please feel free to interrupt me if there's anything I'm saying that you don't understand, you need a little bit more information about. So this is just a reminder, this next slide, that our recipe for the universe today is dark energy about 70%. The latest parameters are 69% from the Planck team. Cold dark matter, 25%, actually about 26% according to their data. And ordinary matter, a little under 5%, of which only about 0.5% is stars and glowing gas clouds, the stuff we actually see. Also, the heavy elements are around 100th of 1%, 10 to the minus 4 of the density of the universe. That's what the Earth and we are mostly made of, these heavier elements, the so-called metals. But they're a very tiny fraction of the mass and energy density of the universe. And in fact, they're the smallest contribution, even smaller than neutrinos. So this picture is supposed to suggest that we're living in a universe that's an ocean of dark energy. On that ocean sail billions of ghostly ships made of dark matter, but we don't see the ships and we don't see the ocean. We just see the beacons on the tops of the biggest masts of the biggest ships. Those are the visible galaxies. We have to deduce everything else from the little bit that we see. Dark matter ships on a dark energy ocean. The technical name, of course, is ΛCDM, lambda for the cosmological constant or some more exotic form of dark energy, CDM for cold dark matter. Now, the reason to take this very seriously is that it predicted, the CDM theory predicted in advance the basic structure of the cosmic microwave background and also the large-scale distribution of galaxies. So these figures from the latest release of the Planck data compare the angular power spectrum of the temperature polarization cross-correlation, and the polarization angular power spectrum with the predictions of the theory. The predictions are those green and red curves, and every point is essentially an independent data point. The agreement is absolutely spectacular. There's no way this could be some kind of coincidence. So, going on to the simulations, astronomical observations represent snapshots of moments in time. Astrophysical theory basically evolves the universe from some early time to later times, up to the present and beyond. So in other words, we produce movies, both metaphorical and actual movies, and I'll show you some movies, that link the snapshots together into a coherent physical theory. Large-scale structure simulations just include dark matter, treating ordinary matter as if it's dark matter, and dark energy. And they show large-scale structure, dark matter halo properties, and they're the basis for understanding galaxies better, for example, with semi-analytic models. So the next slide is one of the Aquarius simulations of a dark matter halo like that of the Milky Way. It's about 1.5 million light years across, about 250 H-inverse kiloparsecs in radius. The Milky Way's visible structure is only 100,000 light years across, about 30 kiloparsecs in radius. So the halo is more than 1,000 times the volume of the visible galaxy, of the bright starry part of the Milky Way. And that's typical for big galaxies like the Milky Way. Their halos are enormous. And for smaller galaxies, the ratio is even greater, much bigger halo compared to the size of the galaxy. How does this fit into the large-scale structure? More or less like this. So this is a slice of the Bolshoi simulation, which Anatoly Klipin and I ran back in 2010, 2011. And it's about 50 million light years thick and 1 billion light years across. You see, of course, the very filamentary structure of the dark matter. Let's zoom in on 1,000th of the volume of this big simulation and just look at a region that's about 100 million light years across, centered on the dark matter halo that would host a large cluster of galaxies. So there's music that goes with this. Can you hear me over the music okay?
Yes.
Good, thank you. So what you see is that there's these long filamentary structures with little blobs of dark matter. Those are the dark matter halos. The smaller ones would host a galaxy or perhaps a pair of galaxies like the Milky Way and Andromeda. The bigger ones would host groups and clusters. The distribution of these structures along filaments is just exactly what we see when we look at the large-scale distribution of galaxies. Now what we're going to do is talk about how the halo of this very large cluster, this halo that would host a large cluster in the center of the image, how that formed. We keep track of the entire history of every halo, tracking all the billions of particles that make up the simulation. And so we know every single halo that merged and merged and merged to form a big structure like this one. And here's that whole history. Every halo you see is going to end up in the one large halo at the end that would host a large cluster of galaxies. You can see that the halos are flowing in along a filament that goes this way, more or less vertically, another one that's coming from the left, another one that's coming from the lower right. The halos are elongated, they're prolate, triaxial ellipsoids, and they're all being shown as the code is finding what the shapes are. And the more massive halos are often quite elongated. We keep track of the halos even after they become subhalos, but we're only showing the halos that are distinct halos, that is, they're not subhalos. So we submitted a paper in February with a tremendous amount of information about several of these large new simulations based on the Planck parameters, and we also compared them with our earlier simulations like Bolshoi and Multidark that were based on the WMAP parameters. So in the upper left corner, we compare the key parameters, sigma 8, the amplitude of the fluctuations, and omega matter for a number of the different simulations, the little dots. The larger regions are the error boxes from the different releases of data. The 5-year WMAP release, the 7-year WMAP release, the 9-year WMAP release, then the 2013 Planck release, the first data release from Planck, and then the more recent 2015 one in red. The black and purple symbols, the little dots, are Bolshoi Planck and Multidark Planck simulations. And the only other simulation that is using the Planck parameters is this Japanese simulation called nu squared GC. They've published some preliminary information about the simulation, but we've done a very detailed analysis of our Bolshoi Planck and multi-dark Planck simulations, and that's what's represented by these additional curves. So among the very many 25 or so figures in the paper, there's the Halo mass function and very accurate fits to it. There's also a graph, the right upper graph, showing the relationship between the maximum circular velocity of halos at different redshifts versus the virial mass of the halos. Notice that the curves are almost the same slope, so they're the same power law, but with a 0-point offset. That is to say, the 0 point rises with increasing redshift. We'll come back to that in a few minutes. Then finally, at the bottom, we're comparing at redshifts from 0 to 8 the number density of halos as a function of the circular velocity of the halos. Notice that there's between 20 and 40% more halos with an even larger increase at the highest circular velocities that would host clusters, comparing the Planck to the WMAP 7-year release results. So the Planck parameters result in a lot more halos, even at redshift 0. And if you look at the higher redshifts, you'll see that the increase is really quite profound. For example, at redshift 8, there's almost 4 times as many 200 kilometer a second dark matter halos using the Planck parameters as using the WMAP 7 parameters. We've now released catalogs and merger trees from all of these simulations. There's 180 stored time steps for Bolshoi Planck, for example. Every halo is identified and all of its properties are given, and also all of the history of all of the halos is now available. So Appendix B of our big paper, the Rodriguez-Puebla, Baruzzi et al. Paper, has all of that information. And it also, of course, points to where these are all released. The paper was just accepted, and it'll be out in monthly notices in a week or so, I think. It's been on the web for some time. The next slide makes an interesting point, that the number density of dark matter halos of about 200 kilometers a second internal velocity, maximum circular velocity, hardly changes out to redshift 3 or 4. It's about the same as it is at redshift 0. That may seem puzzling because we know from the middle top graph that I just showed you that the number of halos as a function of their mass decreases rapidly with increasing mass and more rapidly with increasing redshift. What's happening is that these halos of fixed circular velocity are smaller at higher redshifts. They're at smaller radius, they're lower mass, but they're very dense. They're increasingly dense because they remember the density at which they formed. And it's those two effects that counteract each other that lead to an essentially constant number density. Now, certainly at low redshift, the circular velocity of the halo is closely related to the mass of stars in the galaxy in the center of that halo. Roughly, the stellar mass goes as the 4th power of the velocity. That's the Tully-Fisher law for spiral galaxies, or the Faber-Jackson one for early type galaxies. And there's an intermediate S½ rule. Susan Casson et al. Developed that when she was a postdoc here in Santa Cruz, and she's been working on that ever since, which connects the Tully-Fisher and Faber-Jackson. So you can then use a halo number density to predict, assuming that these relations are the same at higher redshift as they are at redshift 0. You can use them to predict the co-moving mass density of the universe, stellar mass density of the universe, and you get those curves at the top. The blue, red, and black curve just result from making slightly different assumptions about the upper and lower limits of the stellar mass to which these rules would apply. And what you can see is that they cannot possibly be right. If you compare with the observed stellar mass density of the universe, the black points, you're already considerably too high, factor of 2 or 3 too high at redshift 1, 1 plus e equals 2, and an order of magnitude too high at redshift 4. If instead you assume that the Tully-Fisher and Faber-Jackson relations have a changing 0 point, an increasing 0 point at higher redshift, exactly the same way that we showed that the circular velocity mass relation behaves for halos. That was that third panel across the top of the previous slide. Then you get the dotted curve, which is still a little bit high, but a much better fit to the data. As I said, this is discussed in more detail in our paper. Now I want to talk about SHARC. We make very complicated models of the star formation rate in galaxies, but the SHARC idea is putting forward the possibility that star formation is controlled by halo mass accretion when galaxies are on the main sequence of star formation. We're going to show in just a moment that this must be true on average. Now, the radical assumption is that this could be true halo by halo for dark matter halos hosting star-forming galaxies. If that's the case, it's a tremendous simplification of our understanding of how galaxies form stars. The reason that we chose this SHARC name was partly because we're going to put the shark in the bathtub. There are these bathtub models of how stars form from gas in galaxies, the bathtub representing the gas content of the galaxy. And at least for some galaxies, the bathtub stays at just about the same level. New gas comes in, gas turns into stars, other gas is ejected, but the total amount of gas stays about the same, and that's like the bathtub draining and filling at the same rate. Anyway, we're going to put the shark in the bathtub. The key background information you need, though, is the stellar halo mass relation and the galaxy main sequence of star formation. So let me summarize those. The left panel is the relationship between the galaxy stellar mass and the halo mass of a galaxy from what we call abundance matching. Many groups have done this. This is the version from Baruzzi, Webster, Conroy's APJ letter 2013. Their point was that the different redshifts result in slightly different stellar to halo mass relations, but there really isn't that much change from redshift 0 out to redshift 4. In other words, going back to less than 2 billion years after the Big Bang. From then to now, not much change in the efficiency with which gas is converted into stars in galaxies with a given halo mass. Of course, the maximum efficiency occurs for galaxies around the mass of the Milky Way, around 10 to the 12th solar masses, total mass, mostly dark matter. And there, the stellar to halo mass ratio is about 3%. About 15% of the mass of a galaxy halo is ordinary matter, about 1/6, a little less than 1/6, 5% over 31%. And what that's telling us, the fact that we peak out at about 3%, is that only about 1/5, about 20% of the available gas is being turned into stars, even in the galaxies that are doing the best job of turning gas into stars. 4/5 of the gas is not turned into stars. Much of it is probably out in the halo, but not as neutral gas, but mostly ionized hydrogen. The panel on the right shows a remarkable discovery about 10 years ago, starting with a paper from Santa Cruz, Kainowski et al., based on the DEEP survey. And then Maniel Adadi showing that this continued out to redshift 2. And now many, many groups have found the same thing. This is the summary from Kate Whitaker's paper in 2014. So the vertical axis is the log of the star formation rate. The horizontal axis is the stellar mass of the galaxy. And what you see is that at all redshifts, the lower mass galaxies have a star formation rate that's essentially proportional to the stellar mass of the galaxy. In other words, they're on a power law shown by the black curve. At higher stellar masses, the curve flattens out a bit, so there's more of a plateau. But the key thing to appreciate is that at all redshifts, out to 2.5 and even beyond, the star formation rate appears to be governed by the stellar mass of the galaxy. Of course, for stars, the luminosity and the temperature are governed by the mass of the star on the main sequence when the stars are burning hydrogen. And so that's why we're calling this the main sequence of star formation in galaxies. Keep in mind, though, that galaxies at some point can quench and stop forming stars almost entirely. And then they drop far below this main sequence. But when they're on the main sequence, the vast majority of the galaxies, more than 2/3 of them, are within a factor of 2, that is 0.3 decs up or down, compared to the middle of the main sequence. So the main sequence is a very tight relation. Okay, well, taking that into account, let's move on to SHARC. So the box, the blue box on the next slide, shows that if you take the derivative of the stellar mass with respect to the two things that could be changing in the stellar to halo mass relation, namely the halo mass and the redshift, which changes the curves, you get two terms. The star formation rate, the m star dt, is the m star dm halo, the virial mass times dm halo dt. And then there's also the possibility of change with redshift, dm star dm dz, the redshift dt. But if the m star virial mass relation is independent of redshift, then the right-hand term vanishes, and all you have left is the left-hand term. And you can write that left-hand term as the m star dt is m star over m vir d log m star d log m vir, which is actually what the graph plotted, dm vir dt. So basically, it's the slope of that graph times the halo accretion rate that determines the star formation rate. This must be true on average. That's what we just derived. The radical assumption is maybe it's true halo by halo. Now, the first thing we checked to see if that might be the case is what the dispersion is in the halo mass accretion rates. That's shown in the lower left corner. And what you see is that it's hardly changed as you change redshift or the virial mass. It's always about 0.3 or 0.4 decs. In other words, quite comparable to the dispersion around the main sequence of star formation. If you use this relation that I just mentioned to the star formation rate in terms of the slope of the stellar halo mass relation times the accretion rate, you get the lower right-hand panel, which shows that the predicted dispersion in the star formation rate on the main sequence is very comparable to what we actually see. We also noticed, upper left panel, that the mass accretion rate really behaves as a function of redshift very much the way the star formation rate does. So does this actually work? Well, the first thing we did is to check whether it correctly reproduces the star formation rates that we see for main sequence galaxies. And the blue and purple points are the latest data, also the green point. And what you see is that the agreement is really quite good. The prediction is the red curve of the SHARC model. And notice also the blue box on the right. Age matching, the idea that blue galaxies are in accreting halos and red galaxies are in high concentration not accreting halos, that's predicted by SHARC, and it's consistent with observations, as the Heron-Watson papers showed. And also, it's known that galaxy conformity, Guinevere, Kaufman et al. 2013, observed in nearby galaxies, is also predicted by SHARC. So SHARC does really appear to work extraordinarily well as far as we've tested it. Now, as I said, we put SHARC in bathtub equilibrium models of galaxy formation, and we predict things like the mass loading factor and metallicity evolution. The plot on the lower right is the mass loading factor, and that's in very good agreement with observations. So that shows that this whole scheme works remarkably well. We're still in the process of testing to see whether we should really take this seriously. but we've put this forward as a potentially tremendously simplifying way of thinking about galaxies and how they evolve. Okay, moving on. The rest of the talk is mostly going to be about discoveries that we've made in the CANDELS program. CANDELS is the largest program in the history of Hubble Space Telescope. And we've seen three major phenomena in high redshift galaxies. And our simulations actually show all three of these phenomena, and so they give us some understanding of why they occur. Giant clumps, compaction, and elongation. So what's made these new discoveries possible is Wide Field Camera 3, and this is the astronaut installing that camera on Hubble Space Telescope. They took out Wide Field Camera 2, they replaced it with this much larger and better instrument, and the key thing is that it gave us infrared capability. On this slide, you see in the bottom set of panels, labeled ACS, the pictures that we had of galaxies at redshifts of about 2 or 2.5. And with the advanced camera for surveys and Wide Field Camera 3, what we saw was rest frame ultraviolet light from these high redshifts. Because we didn't have the capability of going very far into the infrared, whereas the light of the majority of stars in these galaxies would have been redshifted so that we needed infrared capability to see them. With Wide Field Camera 3, we can see out to about 1.6 microns. So that corresponds to blue light, 0.4 microns, at redshift 3, that is multiplied by a factor of redshift plus 1, 4. Taking us out to 1.6. So we see blue light from galaxies out to redshift 3, and we see the entire visible spectrum out to redshifts of a little beyond 2. And so those upper images are exactly the same galaxies that you see in the lower images, but now we're seeing the full stellar population. And we, in addition to H-band, 1.6 microns, we also have J-band and other data, including also some ultraviolet capability from Wide Field Camera 3. So CANDELS was the project that got the majority of early Hubble time to use this tremendous new data source. We looked at 5 different areas, 2 northern, 2 southern, 1 equatorial, that had been widely studied before. And then we could add a tremendous amount of new Hubble imaging data. So here are the things to keep in mind as you look out in space. You're looking back in time. This is an image that's supposed to represent the cosmic spheres of time. As we look out in space, we look back in time. So we're at the center, that's today. The first sphere is the distance that light has traveled in the 4.5 billion years that the Earth and the Sun have been around and the rest of the solar system. And out to that distance, galaxies haven't changed that much. But if you go out to about 10 billion years ago, and you look beyond that, the images beyond that are all from the Hubble Space Telescope, they don't look like the nearby galaxies. They tend to be elongated and lumpy. At about 13 billion years ago, the first billion years of the universe, we're hardly seeing any galaxies, even with Wide Field Camera 3. And we're waiting for James Webb Space Telescope to let us look a little bit further. But the cosmic dark ages will be pretty dark. And as we go out further, we get to the colorful sphere of the cosmic background radiation about 400,000 years after the Big Bang and the Big Bang itself. So CANDELS focused on the 2 periods that we call cosmic dawn and especially cosmic high noon. The cosmic high noon is the period when most of the star formation is when galaxies are forming stars most rapidly. And that's what we're now seeing for the first time, what galaxies really look like. These are the 5 regions that we have now papered with images from both Advanced Camera for Surveys and Wide Field Camera 3. The yellow regions are the ones that have been covered with those images. Within those larger white regions that we have a lot of data from, but not this continuous coverage with Hubble images. So to compare with these very detailed images of galaxies, we do hydrodynamic galaxy simulations where we follow the gas as it cools, form stars, the stars feed back, and we certainly want to include the effects of supermassive black holes, although that's at a somewhat earlier stage. There's two different approaches that people use, a low-resolution approach and a high-resolution approach. The low-resolution approach, represented by the overwhelmingly large simulations Eagle project, or the Arepo code simulations, the Illustris project. These are large volumes, in the case of Illustris, 100 megaparsec volume, 100 megaparsec cube, with about 10,000 galaxies resolved. But they're not very well resolved. The resolution is only about a kiloparsec. The thickness of galactic disks is a small fraction of that, maybe 100 parsecs. And so these simulations are not really resolving the disks within which many stars form, for example. Also, the simulations are not self-consistent. The winds and feedback and so forth are tuned. And so they, at best, are giving us some picture of how populations of galaxies evolve, but they are doing a good job, better than most earlier work, of simulating the effects of galaxies on their environments. The other approach is to do extremely high-resolution simulations, simulations with resolutions of tens of parsecs. Of course, the three-dimensional difference between 10 parsecs and a kiloparsec is 100 cubed, a factor of 1,000,000 in terms of the number of resolution elements. So these are much more expensive simulations, and so it's not possible to simulate very many galaxies. But the advantages are that they're as self-consistent as we can make them, and we can discover a lot of things about how galaxies evolve and change. And I think two of the leading groups are the group that I'm part of, which uses Qutline's adaptive refinement tree code, the ARC code, and the group led by Phil Hopkins at Caltech. They call their papers Feedback in Realistic Environments, or FIRE. And we're both part of a big comparison project, which I'll talk about at the end if there's time. So this talk is about these high-resolution simulations. So both gas and small galaxies come in along filaments, usually 3 filaments, to a region where a galaxy is forming right at the center. We've run a number of simulations, four series of simulations that we're calling generations 1 through 4. Generation 1 was lower resolution, higher mass galaxies. I won't talk about those except just to show one slide. Generation 2, 3, and 4 were all run with exactly the same initial conditions. They were drawn from that red circle, red elongated region in this diagram, showing virial mass versus circular velocity. And all we did, it's those colored dots, the blue dots. All we did in choosing them, the blue dots, I guess, and the black dots, was to have a uniform distribution in log mass from about 2 times 10 to the 11 to 2 times 10 to the 12th solar masses for the dark matter halos. These were run to redshift 1 to save CPU time, although we're now running some to redshift 0. So this slide shows at the top face-on and edge-on gas distribution in our lower resolution, larger mass simulations, and the same simulation shown at the same time step about redshift 2, 2.3. And then we use our sunrise code to convert these simulated galaxies into what we would see with Hubble Space Telescope. So in other words, what the stellar galaxy would look like. And at the bottom, on the left-hand side, are 2 observed redshift 2 galaxies, a sort of linear one and a face-on spiral, it looks like. And on the right-hand side are these same simulations that you see pictured above, but degraded in resolution to correspond to what Hubble would see. And what we hope you see is that there's a good deal of similarity between the observations and the simulations. We now have tens of thousands of images that we've analyzed, and so we can say with greater assurance that we're beginning to understand what these observations are telling us, and we're starting to make detailed comparison with the simulations. One of the keys to our Generation 3 and 4 simulations is to include radiative feedback. This is the Rosette Nebula, a nearby nebula in the Milky Way, and you see this typical pattern of some O stars in the middle that have cleaned out a large region where there's very little gas and dust. The light pressure and the winds from these very bright stars tend to clean out these regions and form around them regions that are protected by dust where planetary systems could form, as in the so-called pillars of creation. In order to resolve and treat this kind of phenomenon, you need to have resolution that's only 10 or 20 parsecs, because the size of the star-forming regions is only a few times that. And so this is not something that can be realistically done unless you're running simulations of these high resolutions, which is what we're doing and also what the fire group are doing. So this is examples of what these galaxies look like if we could see them up close. The left is our number 27 simulation run to redshift 2.1 without radiative feedback, and then the same exact initial conditions run to the same redshift with radiative feedback. And you see that with radiative feedback, they're more elongated. They don't have as many small lumps, but they have about the same number of large lumps. That's what our detailed study has shown. We published that paper. First author was my graduate student, former student, Chris Moody. So radiative feedback, fewer stars, more elongated, and also fewer small clumps. When we didn't include the radiative feedback, we were overproducing the number of stars, the stellar mass, for a given halo mass. That's the blue points on the left. Including the radiative feedback, we're doing a much better job. We're very close to the Bernoulli-Wechsler-Conway stellar to halo mass relation. This is the gas distributions, and again, with radiation pressure, you see fewer small clumps, but about the same number of large clumps. Now, this is that paper by Moody that I mentioned, where we actually compared the simulations in some detail. Now, this is images of real galaxies from Hubble Space Telescope at redshifts 1, 2, and 3, showing just how remarkably clumpy they are. The detailed paper on this came out at the end of 2015. The first author is Yi-Ching Guo, a postdoc here in Santa Cruz. But there are many references here to papers by the Elmagreens and others, which have been making this point for many years. The advantage of the new paper is that it has statistics. So the left-hand panel is from that new paper, and it shows that at redshifts 2 to 3, about 60% of all star-forming galaxies are clumpy. That means that they have off-center clumps. We don't count a central lump as a clump. They have off-center clumps of masses of at least 10 to the 8 solar masses, 100 times more massive than the highest mass globular clusters. And this is ubiquitous. A majority of star-forming galaxies at these redshifts have these kinds of massive clumps. That remains true down to redshift 1/2 for the lower mass galaxies, up to between 10 to the 9 and 10 to the 9.8 stellar mass. For intermediate stellar mass galaxies, up to about the stellar mass of the Milky Way, this is true for about 50% out to redshift 1 to 1.5, and 40% at redshift 1/2. And for high mass galaxies, it drops to about 20% at redshift 1/2, but it's still nearly 40% at redshift 1 to 1.5. So this is a very important phenomenon, this clumpiness. Another thing about the clumps is shown in the right-hand panel from an old paper, 2012. We actually have much more detail, and a new paper is being prepared. First author will again be Yi-Ching Guo. What you see is that at large radius, the clumps are blue, and as you move into smaller radius, the clumps are redder. And that's exactly what we see in the simulations. On the left-hand side is those same Hubble Space Telescope observations, and on the right-hand side are our simulations. And what you're seeing is, with the big black crosses, how the simulations are showing this trend, red on the inside, and then as you go to larger and larger radii, bluer and bluer. The purple dots are ex situ clumps. That means clumps that formed and then merged with the galaxy as minor mergers. And of course, those don't follow the same pattern when they're at large radius. They've already formed their stars. There's a new paper on this led by Nir Mandelker. Moving on to the so that was the clump story. Moving on to the second story, which is the compaction story. We used to think that galaxies grow in size as they grow in mass, because at low redshift there's a tight correlation, especially for early type galaxies, between the radius and the mass. Larger mass, larger radius. This turns out not to be the case, that this is an evolutionary trend. Instead, there's very good evidence that galaxies often undergo a process of dramatic shrinkage in the radius that encloses half the light. So this plot that is on the screen now has a measure of how compact the galaxy is on the horizontal axis, more compact on the right, and increasing specific star formation rate divided by stellar mass, on the vertical axis, remember, increasing downward. So the lower left corner is star-forming galaxies that are not very compact. We call them diffuse. The lower right corner is more compact star-forming galaxies. Upper right corner, compact quenched galaxies, that is not star-forming. Upper left, increasingly non-star-forming galaxies that are fairly diffuse, not so compact. We call two different tracks, the fast track and the slow track. More massive galaxies tend to follow the fast track. They start as fairly large galaxies, but then the half-light radius dramatically shrinks, and they become what we call blue nuggets. The blue nuggets turn into red nuggets, that is, they quench and form few stars after 100 or 200 million years. Then they grow in size, apparently mainly by minor mergers. The slow track, which is what spiral galaxies like the Milky Way seem to follow, is galaxies that start fairly large and diffuse, and they become more centrally concentrated as more and more mass flows into the center and forms a lot of bright stars there. But they remain fairly large, diffuse, and typically spiral objects. So two very different tracks, the fast track and the slow track. How do we know about this? So what we did, this was in the first paper led by Guillermo Barro. There's now half a dozen of these papers. We looked at the same cosmic volume at 6 different redshift intervals. And we tracked how the galaxies moved through that diagram that I just described to you. And what you're supposed to see is that the galaxies start at high redshift, hardly populating the upper right corner, beginning to populate the lower right corner, and populating fairly heavily the lower left corner. And there's a motion, as in that diagram, from the lower left to the lower right, and then into the upper right. And we now have a lot more data, and we quite convincingly can show how this trend is developing. And the most recent paper submitted by Guillermo Barro is on the archive, submitted in 2016. But this pattern does appear to be the way things work. And we see exactly the same thing in our high-resolution simulations. The top 2 panels represent 2 examples of the fast track. The lower 2 panels represent 2 examples of the slow track, galaxies that never move into the lower right corner. So in the upper right corner, you see galaxies that were fairly diffuse, and then on a fairly short time scale move over to become quite compact, and then slow their star formation rate and simultaneously grow. These are from the paper led by Adi Zolotov, published last year, which has many more examples. And we're willing to share all of the examples with people who contact us. So let me now summarize how this works in individual simulations. These are cartoons by Avishai Dekel from the Zolotov paper. And what we're going to do is look first at the inner kiloparsec and then at the inner 10 kiloparsecs. So what happens in the inner kiloparsec is that there's a rapid inflow of gas in this regime that we call compaction between the two dashed vertical lines. The gas flows into the very center of the inner kiloparsec of the galaxy, and there's a rapid increase in the numbers, the mass of stars in that region. Before the compaction process, the inner part of the galaxy is dominated by dark matter. Afterward, it's dominated by stars. So there's this rapid increase in the number of stars just in the innermost region. And that means that it's because of this rapid inflow of gas that the effective radius, the radius that encloses half the light, shrinks. Now, if you look on the larger scale of essentially the whole stellar galaxy, you see that although star formation ceases in the inner kiloparsec after the compaction phenomenon, star formation continues out to larger radii, which are still dominated by dark matter. There's a gas inflow, and then the gas gets used up and converted into stars, and the galaxy starts to quench typically. So let's look at how this actually works in an example simulation. So this is one of our simulations. It happens to be number 7 with radiative feedback. And what we're going to do is look on the left at within 5 kiloparsecs, and then the lower left within 1 kiloparsec. And on the right, you're going to see how the galaxy evolves. This all goes by pretty quickly. Here goes. So the galaxy started out fairly elongated. It's now turning into a more or less normal spiral. You can see that the disk is becoming more elongated, edge on. The gas disk is quite elongated, edge on. And face on, you see, especially in the gas, spiral waves. So we've now talked about 2 different phenomena. The first one was clumps, and you also saw some clumps here. And then we talked about compaction, this process where galaxies, during their evolution, especially the more massive ones, can have a period where they rapidly shrink. Actually, before we move on, let me just summarize that rapid shrinkage story. So the more massive galaxies follow this bottom curve. The color codes redshift. So red is redshift of about 5, and then orange is redshift of about 2.5, about 3.5. And so you see at these higher redshifts, the more massive galaxies undergo dramatic compaction events. We're going to have to wait for James Webb Space Telescope to see a lot of this. The lower mass galaxies undergo compaction that's less dramatic. They drop in, the radius is not a factor of 2, it's more like about a factor of 0.7 or something like that. And it occurs at lower redshift for the lower mass galaxies, a downsizing phenomenon. But as the recently published paper by Sandro Tecchella et al. Showed, it's quite consistent with observations. There's also a similar comparison with observations of our simulations and other group simulations in a recent paper led by Peter van Doken. Moving on to the last of the topics, the elongated nature of the star-forming galaxies. So this is the paper led by Arjen van der Velde. It came out at the end of 2014. There's an independent analysis by Takeuchi et al., which was published in APJ last year. And both agree that for 10 to the 9 to 10 to the 10 solar masses of stars, galaxies are predominantly elongated down to redshift of 1.5 or even 1 for the lower masses. How do we know that? It's from looking at the distribution of axis ratio, short axis divided by long axis. And you see in the lower left panel of the upper part of this diagram, the distribution for the 10 to the 9 to the 10 to the 9.5 solar mass galaxies at redshift of, I guess that was 1.5 to 2. And what you see is it peaks at about ratio of 0.3 and rapidly falls beyond that, with very few having axis ratio bigger than about 0.7. And a sphere, of course, would have axis ratio of 1, and a disk seen at different orientations would have axis ratios from 1 to whatever the thickness of the disk is, 0.2 or something. But what we're actually seeing is a predominance of very low axis ratios. That could only mean that these galaxies are shaped not like disks or spheres, but rather like hot dogs or zucchinis. So not like disks, not like spheres, but like zucchinis. Or how do you say that in Portuguese? Anyway, so
Abobrinha.
Abobrinha.
Okay, good. So on the left hand, the upper part of the image is the dark matter distribution, and you see how elongated it is. That's been known for many years that the dark matter is elongated. Classic paper on that is my former student Allgood's paper 2006 on the elongated nature of dark matter halos. They tend to align, of course, with the dark matter filaments. And in the right-hand part of that, you see how the stars are organized just like the dark matter, elongated just the same way. So this is from our first paper on this. The simulations were done by Daniel Severino, and Avishai Deckel and I helped to write the paper. And so there you see again how the stars and the dark matter are very much aligned. On the right-hand side, what you see is that the galaxies are elongated as long as the ratio of dark matter mass to stellar mass to dark matter mass is less than 1. That's the horizontal dotted line. When the stellar mass becomes larger than the dark matter mass in the inner kiloparsec, then the galaxies become rounder. So this is a phenomenon where the dark matter is governing the way the stars form, and also, of course, pre-existing galaxies that flow in along the filament. The stars basically behave just like the dark matter. They're supported, both the dark matter and the stars are initially supported by anisotropic velocity dispersion, not by rotation. And then as more and more material comes in with some angular momentum, it becomes more and more supported by rotation, and that explains the conversion into diskier structures. And this is described in some detail in a paper by Matteo Tomasetti, which was just accepted for publication. Tomasetti is a postdoc working with Avishai Deckel. So this is a summary from the Tomasetti paper. And it also makes the connection with the compaction phenomenon. It's in the compaction phenomenon that the stars become gravitationally dominant. That is, they become the majority of the mass in the inner part of the galaxy. And what we just showed you was number 28 of the Vela simulations, and with the dark matter on one side and the stars on the other side of that image. And this shows the compaction phenomenon precisely for that galaxy. And the compaction occurs at about redshift of 1.5. So very much within the possibility of observing this with Hubble Space Telescope. Now, as I mentioned, we're making predictions that this phenomenon is ubiquitous, that essentially all galaxies seem to undergo compaction and start out as elongated, oriented along the cosmic web, and then become much more circular or round. And to see the phenomenon at higher redshifts, we're going to need further infrared capabilities, and that's what we're going to get when James Webb Space Telescope launches, now scheduled for the end of next year, 2018. So instead of having only capability of going out to about 1.6 microns, NIRCam will actually give us images out to 5 microns and spectroscopy out to 5 microns. And there's a mid-infrared instrument that will give us a lot of data out to 28 microns. So James Webb Space Telescope is going to open a very important new window, not only at the highest redshifts, but at these intermediate redshifts when most galaxies are going through these important phenomena. Last topic, how seriously can we take these simulations? Our simulations produce all of these phenomena, but we're the only group that are doing this. No other group, in fact, has succeeded in showing any one of these 3 phenomena. And in fact, there's a recent paper, Optopic is the first author, and then Phil Hopkins, where they basically, the FIRE group is basically saying that they're not finding these clumps. And I think that means that there's a problem with their feedback. It may be too strong. But it's very worrisome when only one group is finding these results and other groups are not. So are the simulations reliable? Is the resolution adequate? Is our feedback being done correctly? And we have some understanding from the simulations, but how seriously can we take them until other groups start to get similar results? So in order to advance the whole field, Pero Mandau and I started the Assembling Galaxies Resolved Anatomy, or AGARA project, 4 years ago. A number of leading people in the field are members of our steering committee. Ji-Hoon Kim has played a tremendously important role as the coordinator for this project. He was a postdoc here in Santa Cruz, then at Caltech, and most recently at KIPAC at Stanford as an Einstein Fellow. There's about 100 astrophysicists from 50 institutions in 8 countries using, actually now it's 9 simulation codes. We agreed on initial conditions for cosmological simulations and also an isolated spiral galaxy at redshift 1. All groups are using the same ultraviolet background, the same cooling function, and we're comparing the simulations with exactly the same tools, the YT code. That's ytproject.org, yt-project.org. That's a volumetric analysis package, which can read all of the outputs from the different simulation codes. Here's the paper that outlined the entire project, published at the end of, beginning of 2014 in AppJ Supplement. We have many working groups, but I'm going to just show you some results from the isolated galaxy simulation. So here you're seeing 9 different codes. The gas surface density maps edge on and face on. The projected temperature maps edge on and face on. But I'm not supposed to show you these. And in fact, these are not the latest ones. But we're nearly ready to submit our paper on this. The paper should be out later this summer. Here again, all 9 codes are being compared in different ways. Again, this is quite preliminary. What you notice, though, is that they're really different. And so we're learning a lot about how the different codes, starting from exactly the same initial conditions and making as much as possible the same assumptions, are reaching somewhat different conclusions, and we're beginning to understand why. And that's what's going to be discussed in the paper that we're finishing now. Well, that's what I wanted to tell you. Here's my summary. Let me leave that up, and I think I finished exactly 1 hour.
Okay, thank you very much. So questions, please. Questions?
I realize a lot of material here. I hope it wasn't overwhelming.
Yeah, it was a lot of material.
Now, I sent you earlier a video of a presentation that I did where I actually included a few more slides, and also separately all the slides. I posted them on my webpage. So if people want to absorb this more slowly, there's a video of me giving a similar talk about 2 months ago at the University of Utah, and all of the slides, including the ones that I omitted, are on the web, and I think I sent that information to Luis da Costa.
Okay, I will pass them along. And I have a question. You said that the difference about different codes, and what are you going to learn about the assumptions of the baryon physics? As you said, too much feedback or not, and how do you think to put together these new observations from James Webb and the simulations would improve the baryon physics knowledge?
One of the things, so of course the key thing that we're going to get from James Webb is the ability to see galaxy formation out to higher redshifts. When we think that the phenomena that we're seeing, the clumps, the compaction, the elongation, are going to be happening for galaxies that are more massive today. They would have gone through these phenomena, we think, at an earlier stage, but of course we might be wrong. So one thing that we're going to do is we're going to see if the simulations that we're doing and the predictions that they make are true. James Webb is going to have another capability that Hubble doesn't have, and that is it has thousands of little shutters, and they can basically give us the possibility of getting spectra for many, many galaxies, and also out to pretty far in the infrared, and also for galaxies that we can resolve, we can basically have integral field unit observations. So we'll get spectra across a wide range of wavelengths at a number of different places in a given galaxy. And these will give us much more dramatic tests than we've been able to do so far from ground-based spectroscopy of the internal kinematics and chemical evolution of these galaxies, all of which, of course, are predicted by the simulations. Now, more generally about the simulations, the simulations are making the same assumptions about large-scale issues and also issues that are basically things that you dial in, like the initial mass function, the metallicity production, and so forth. But as far as things like star formation and feedback, those occur on scales much smaller than the best resolution, even parsec resolution. Star formation occurs on much smaller scales than that, AU type scales, astronomical unit scales. So it's not possible for the different codes to adopt the same assumptions regarding feedback and star formation. Those are code dependent. And one of the things that we're going to learn by comparing the codes with each other and with the observations is which of these assumptions are better. I gave an example during the talk where I mentioned that this recent paper from the FIRE team says that they're not seeing any long-lived clumps. They see no stellar clumps at all. They see gas clumps that only live about 10 million years. Well, they're not seeing what the universe is producing. And that's a problem for their simulations, in my opinion. And very likely it means that they have too much feedback, because it's known that if you turn up the feedback too much, you destroy the clumps. But the clumps are there. That's a ubiquitous phenomenon. So that's an example where by running the same code with same initial conditions, but getting different results, and then comparing with observations, we can see which are better and which are worse. So those are all the kinds of things that the Agara project is going to help us with, we hope. I hope that answers the question.
Yes, thank you. Okay, more questions?
If people think of questions later,
I have one.
My email address is just my first name, Joel, @ucsc.edu, and I'll try to answer all questions.
Okay, but maybe you could say something a little bit about the feedback of AGNs in the simulations? You mentioned briefly in your slides, but
So-
can you give some outline?
So in our simulations and also in the fire simulations, we have not yet included feedback from AGN.
Ah, okay. Okay.
So what was done in low-res simulations, including those that I mentioned, the illustrious and Eagle simulations, is a very simplified feedback prescription.
Yeah.
Basically, there's a simple assumption, Bondi-Hoyle accretion, which we know isn't valid, but which is nevertheless used to predict the rate at which mass is accreted by the black hole. And then it's assumed in these codes that all of the energy from the black hole, the 10% or so of m dot c squared that's radiated, all of that is simply thermal energy. It's thermalized. They don't take into account jets. They don't take into account radiation. It's all basically just thermal energy. And if your resolution is a kiloparsec, that's probably not a terrible assumption. But if you're running simulations with resolution of order 10 parsecs, that's a horrible assumption. We've written these codes to be able to track the effects of radiation, photoionization, and all of these phenomena. And so we need to be able to do that also for the AGN. But the amount of radiation that these AGN can put out is so large that we have to split it in different directions, and we're working on coding all of this, but it's going to be at least a year before at least the group I'm part of has results that we would take seriously. So it's something that we're working on, and it's a major project for the next year.
Yeah, tough job. Okay, thank you.
Unfortunately, for the more massive galaxies, it's absolutely critical. Very likely, it's an important part of the story as to why these galaxies quench.
Yeah. Yeah.
Okay, Mark.
Thanks again.
Okay, if you don't have more questions, let's thank Joe again for this very nice talk. Thank you very much.
Sure, glad to do it.
Okay, so see you all soon, and thank you.
Sure. Bye-bye.
Bye-bye.
All right.
Bye, Joe. Thank you very much.